Good afternoon. Today we will continue course Geomechanics for Geologists and we will discuss lecture number 8, Input Data for Geomechanical Modeling. Our lecture plan is below and we will discuss today 1D geomechanical workflow, log analysis, core analysis, drilling events, well researching and database. First topic is 1D geomechanical workflow. So the slide presents a typical workflow for building of a 1D geomechanical model. This workflow includes the stage of analysis as well as the necessary calculation of mechanical properties and stresses. As you can see here, the stage of data analysis is very important. And it's very important for our geomechanical work, and also predetermines the correctness of entire geomechanical modeling. This is in turn affects the economic efficiency of well construction and the reduction of unproductive time. The slide shows the calculation stages of building of geomechanical model. At first, the vertical stress and pore pressure are calculated. Secondly, the horizontal stresses are calculated based on the data of the borehole stability is calculated. And the main parameters for calculating borehole stability is shear fracture gradient and fracture gradient. The model is then calibrated on various materials such as drilling events, caliper, gas readings, cuttings, cavings, etc. In this presentation we will talk about the preparation of initial data for geomechanical modeling. As a rule, source materials are a chaotic set of disparate materials that need be systematized and collected in a form that will be convenient for geomechanical specialists. As shown in these pictures, the data must first be sorted, then distributed according to some characteristics. For example, the core needs to be collected in a single table for all wells sorted and filtered by core study types, layer direction, lithological type, and so on. After that, the data must be analyzed for quality. For this purpose, various types of analysis can be used. For example, histogram analysis, the use of cross plots, estimation on boundary values, etc. The slide shows the main initial data for building geomechanical models, and priorities are highlighted in colors. The most necessary data are shown in red, of which the geomechanical data will be incomplete or incorrect. In yellow zone, recommended data that can be used for significantly improve the geomechanical model. Accordingly, the optional data is shown as green zone. So the red data categories refer to reservoir and seal information, in particular stresses and pore pressures measurement data. In addition, the necessary data are other results of core studies, daily drilling events, end of well reports, special well logging complex including acoustic, density, gamma, caliper, and other logging methods. The yellow category zone includes various lithological and petrophysical reports, mineral model, drilling parameters, etc. So optional input data include seismic interpretation data, well temperature information, prediction cube, pore pressure dynamics, etc. Nevertheless, all this data set for geomechanical modeling must be prepared and checked in order to avoid various errors and accuracies. The next topic is log analysis data. Among the wide range of logging data, critical and non-critical logs can be distinguished for constructing a geomechanical model. Critical data includes acoustic, density, caliper, resistivity, and microimagers. Non-critical data includes nuclear magnetic resonance, neutron methods, spontaneous polarization, photoelectric methods, so on. Thus, caliper measurements in geomechanical model are used to calibrate wellbore stability. Gamma logging is used to cut off the shale line for the purpose of the further calculating pore pressure using the Bowers and Eaton methods. Acoustic and resistivity methods can be used to calculate elastic and strength parameters as well as porosity and permeability. Microimager is used to assess rock bedding elements as well as the direction of breakouts and tensile failures in order to determine the direction of the maximum principal stress. It is important to note that each of the above methods is characterized by its vertical resolution and depth of research. Thus, electrical logging is characterized by the greatest depths. Neutron and radioactive method have a lower resolution. Density and acoustic logging methods, which plays the most important role for geomechanics, have a reason vertical resolution and depth. For this reason, is need to do a careful validation of the initial density and acoustic logs for modeling. These methods will not work in interval with an increased borehole diameter, such as cavern and cases. This is due to the fact that they will not show the characteristic of the rock, but the characteristic of the saturating mat. The acoustic and density log methods in this case should be corrected, taking into account methods that have greater depths. For example, using Faust's equation that involves replacing acoustic logs through resistivity. The slide with typical log values shows typical readings for different logging methods. The highest reading of gamma logging are characterized by clays and oil source rocks with a high content of total organic carbon, and lowest readings are characterized by coals, carbonate rocks, anhydrites, dolomites, and other rocks. As the resistivity, carbonate rocks, salt and coal, igneous rocks have very high readings, and water-saturated reservoir has minimal readings of resistivity. Also, Caliper anomalies can have both a negative and positive sign. As for negative sign of Caliper, that is clear is characterized as a rule by reservoirs. Positive anomalies are characterized by rocks with washout and breakouts. We will talk about Caliper anomalies in a few slides. So acoustic and density log are interrelated, and the highest density values are characterized by dolomites, granites, tight sandstone, and lowest coals and salts. Let's go to main preprocessing log operation. They include log checking, so interruptions, etc. Log normalization, the log's reading will be similar in the same interval as sandstone of shales. for the different logging tools, minimizing tool calibration and scaling difference. Therefore, the log data set would be homogeneous and consistent for all well includes in the analysis. Log correction, which take into account the influence of the caverns, gas fluids on log readings, and log synthesis of restoration. This is restoring of necessary methods, especially density, P and S wave acoustic. Visual validation of logging data. This is one of the first steps. This slide shows examples of logging curve disruptions. These disruptions must either be interpolated or repaired by other methods. The most optimal way is replacing of disrupted intervals of P wave and S wave slowness and density on the values of synthetic curves. The log normalization is the next point. This is a vital procedure before getting into any log evaluation in order to have a reliable petrophysical analysis. It allows you to equalize curves from different wells by stratigraphy, lithology, depth, etc. Therefore, normalization allows you to be sure of the correct distribution of data from well to well. When input logs data displayed and plotted at histograms, some differences in logging tool calibration and curve scaling can be noticed, especially when log data was compared for each well against the other. When log normalization is performed, the log's readings or values should be similar in the same intervals for different logging tools. It minimizes difference of tool calibrations and scaling. Therefore, the log data set would be homogeneous and consistent for all well. Normalization at no homogeneous phases, marine environmental shale, tight limestone, ungraded layer, etc. is preferable as a reference data. The example of normalization taking into account the reference layer is shown on this slide. In this case, the reference layer is a homogeneous marine environmental shale which has a consistent bedding within the entire field and is a seal. As you can see on the left part of the slide, the original curve was DTP, DTS and density log had a different distribution. But after log normalization for interval of the reference layer, this curve began to have a similar distribution. This is one more example for P and S wave slowness and density normalization for layers. The histograms can be common and cumulative. The cumulative histogram are used to extract a probabilistic value such as P10, P50 and P90. An example are given here. In addition to normal distribution, there can be many different distributions in geomechanics. For example, binomial, exponential, Poisson, Fisher, etc. Examples of extracting probabilistic values for the main and secondary seal and reservoir are shown on this slide. Another method of logging correction is the fluid substitution. The importance of fluid substitution lies in the fact that in gas-saturated rocks the velocity of P and S wave are underestimated. This in turn leads to underestimation of the Poisson ratio, and then underestimation of Poisson ratio leads to a decreased horizontal stress. The understated horizontal stress gives a false impression of the drill window of narrowing this drill window. This fluid substitution is very relevant for a gas-saturated reservoir. So having information about the composition of fluid and the mineral density in each section, it is possible to accurately determine the porosity of rocks along the density curve in an interactive way. Then the fluid of the pore space is replaced with water, and new density values for porosity and mineral density of rock are calculated. The P-wave slowness and the fluid substitute density curve is calculated. Since the connections are established on logging data in water saturated interval and clays, the calculated DTP curve is obtained by substituting of water. The most popular method for fluid substitution is Gassman's method. The restoration of curves, especially in well washout interval, is carried out taking into account logs with the higher depths. One such example is the use of the Faust equation, which allows you to restore the acoustic curve taking into account the resistivity. At the same time, the resistivity has a greater depth resulting than the acoustic logs. And in washout and cavern interval, the resistivity value is more real than acoustic one. Please note the difference between a synthetic and recorded log. The difference between them is observed mainly in interval of caverns. This shows that in the cavern interval the real density is underestimated due to the fact that cavern is insufficiently wide, and density log characterized not the properties of the rocks but the property of the drilling fluid. A similar example, but using acoustic logs. Another reason for restoring curve in the interval of the absence in their using for the calculation. For example, density cannot be used for the calculation of overburden pressure if it partially represented by. The bulk density log must be complete over the entire section of the well. We discussed it into lecture 01. This slide shows the restores density curves using the Traugott equation. For acoustic and density logging methods, normal compaction trend line can be used for additional quality control, which for all wells of the same field must have the same coefficient for their construction. Separately, it is worth focus on the cross-dipole acoustic logging. The feature of shear waves is the polarization. Due to the polarization of shear waves, they are divided into the fast and slow shear waves. The least negative time shift corresponds to the polarization direction of the fast shear waves, which is also SHmax azimuth, and the most positive time shift corresponds to the polarization of direction of the slow shear wave, which is the SHmin azimuth. From the point of view of shear wave propagation in the rocks, four types of rock can be distinguished: homogeneous, isotropic, heterogeneous, isotropic, homogeneous, anisotropic, and heterogeneous, anisotropic. Accordingly, the direction of fast and slow shear waves can be used to estimate the maximum horizontal stress azimuth. The slide shows examples of comparison of Ross diagram for cross-dipole acoustic logging and formation microimager. As you can see here, the data are consistent with each other. The azimuth of maximum horizontal stress in all four wells corresponds to the direction southeast and northwest. The next object for analysis is microimager. Borehole image log can be also used for identify wellbore breakouts and tensile failures. For a vertical or near vertical borehole, the maximum horizontal stress orientation is aligned with the direction of drilling induced tensile failures and is perpendicular to the direction of borehole breakouts. The figure displays a section of ultrasonic borehole imager log data processing for a vertical well. The rows diagrams within the maximum horizontal stress orientation for individual wells can be plotted for the comparison with a fault stripe. Another important input data for geomechanical modeling is Caliper. The main types of damage on Caliper and imager are next. Washouts that are in an open hole section is larger than original hole size or size of the drill bit. They can be caused by excessive bit velocity, unconsolidated formation, stresses, or mechanical damage of chemical interaction between shales and water. Second is breakouts that refer to compressive failure in a borehole caused by non-uniform horizontal stress exceeding the compressive strength. And final case it. This is a small diameter canal worn into the side of a larger diameter borehole. This can be as a result of a dogleg. We will discuss dogleg in the next part of lecture. If you build a correlation graph between the arms of Caliper C1 and C2, then within the colored zones you can distinguish various types of borehole destruction. For example, ovalization, K-seats, tight hole, engage hole, etc. types. Though the borehole deterioration with time is a serious problem, especially for clay stones. Wellbore breakouts increase greatly for the Caliper logs performed number of hours later compared to Caliper log run earlier in the same depth interval. This is mainly caused by rock relaxation of creep. Rock strain increases with the time even under a constant loading stress. Therefore, when subjected to a constant stress even smaller than the rock strength, rock deform and may eventually fail over time due to creep. This effect must be taken into account already at the stage of analyzing the geomechanical initial data. Another type of input data is gamma logging, which is used to recalculate clay content. Clay content in turn can be used in the future to calculate the friction angle. The internal friction angle has a serious impact on the borehole stability, which we have already discussed in detail in the lecture number 06. 4D seismic monitoring is the development of traditional seismic methods, which includes not only obtaining spatial data on geology and geomechanics as a certain depths, but also temporal changings of these parameters. The main purpose of 4D seismic monitoring in geomechanics is to track changes in underground condition, in city condition. For example, to track the waterfront to prevent seal disintegrity. Distributive temperature sensing is one of the rest seal integrity monitoring methods, and temperature anomaly makes it possible to identify the limits of fracture propagation of ejection well and prevent fracture breakthrough in the overlying and downstream intervals. Let's discuss main heat transfer mechanism in oil-gas system. First, conduction is the process of the heat transfer through the material without any movement of the material itself. It occurs at the molecular level where heat energy is transferred from faster moving molecules to slower moving ones. This type of heat transfer characterized for seals. Convection number 2 heat transfer method is a heat transfer that occurs due to the movement of fluids, liquids of gases. This movement can be due to inherent forces caused by density difference. For example, it characterized in a reservoir. And at third, it is a radiation. Radiation is the transfer of heat energy through the electromagnetic waves, such as radiation. Another method for the detection of the limit of fracture propagation is the injection well noise logging. If we combine all the above, then all logs can be evaluated in terms of their completeness in offset wells. An example is shown in the slide. Green shows interval with real log readings. Synthetic intervals are shown in yellow. Such graphs make it possible to select the most representative wells from the point of view of geomechanical model. The core analysis is next part of our discussion for today, next topic, and core analysis should start with the combined tables. An example of such tables is shown on this slide. As a rule, they combined all the data of all core investigation, including geomechanics, petrophysics, geochemistry, and another method. For an express assessment, you can build a matrix of factor. The factor matrix includes core-core type correlation for different type of core investigation. In the same table, you can show the coefficient of determination and highlight them with color. In addition to core-core correlation, there are correlation core-log and log-log. They can be filtered by different lithology, stratigraphy, and values. This slide shows the real correlation of core-core between the dynamic and static Young modulus, density and strengths, P and S wave slowness, velocity of P wave, and density. Colored dots illuminated by different stratigraphic layers. A distinctive feature of clastic rock is their anisotropy. This is especially a characteristic of clays and oil source rock. The anisotropy of rock must be taken into account using transversal vertical anisotropy medium. As for core specimen on this slide, all moduli decrease significantly with increasing of clays and total organic carbon content. The horizontal samples that parallel to bedding are stiffer and stronger than vertical samples that perpendicular to bedding, and at last the difference between horizontal and vertical stiffness values increases with increasing of clay and total organic carbon, reflecting the contribution of these parameters to elastic anisotropy. So the static investigation different confining pressure can be used to build more failure envelopes. They make it possible to determine the cohesion and friction angle, which are calibration parameter for the geomechanical model. Based on a set of core studies including geomechanics, thin section studies, mineral composition, component composition, porosity, permeability, and another factor, the mechanical facies can be identified. For example, as shown in the figure, 8 mechanical facies have been identified based on research which differ from each other in composition, Young modulus, Poisson ratio, and stress-strain charts. This slide and next slide show examples of calibrating log curve to core data. The next topic is drilling events analysis. The drilling events analysis include cavings and cutting reports, mud weight reports analysis, daily drilling reports, cementing reports, end-of-well reports, and trouble plot construction. This summary table shows a different type of well failure and shape of cuttings. Among such types are enlarged wellbore, collapsed wellbore, stable wellbore, rubble zone, fracturing, and ballooning. Cuttings are an important indicator for calibration of the geomechanical model, so therefore the study of cuttings is a very important task. The cuttings should be described in terms of shape, type, size, composition, and other visual parameters. As shown in the previous slide, the shape of the cuttings can significantly determine the borehole failure type. For example, the collapse type is characterized by angular cuttings, which is formed in the process of shear failure. The next step is in this process of analyzing drilling events is analysis of drilling incidents. The first incident we will consider, this is dogleg, which characterizes the effect of the drill string on the curved section of the well with the formation of the so-called K-seats. The next serious incidents are stickings, which can be divided into mechanical, indifferent, and differential sticking. The comparative picture between mechanical and differential sticking on this slide. Differential sticking is a relevant issue encountered during drilling, arising from the differential pressure between the hydrostatic pressure of the drilling mud and the pore pressure. This situation occurs when the hydrostatic pressure exceeds the pore pressure, leading to the drill string being forced into the filter cake of a permeable formation. Secondly, mechanical sticking occurs when components of the drill string, including drill type, heavy weight drill pipe, drill collars, drilling bits, so this can happen due to mechanical factors such as cuttings, debris, excessive cement of alterations in the geometry of the drill string, making it impossible to extract the stuck parts without causing damage to the drill pipes. This and the following slides are so-called trouble plots. There are plots of drilling incidents which shows all major drilling incidents including overpulls, stickings, losses, increased cutting zones, etc. The trouble plot are need to calibrate the geomechanical model and understand the depths at which these drilling events occurred. For convenience, the trouble plot are made different, for example, which this slide especially shows 1D trouble plot. This trouble plot is the following type of plots with an indication of running hole operation. This is a stick chart plot which shows several wells with the indication of the casing. At different depths, the structures show the most striking events that were encountered during drilling. This is necessary when designing new well. The following graph shows the distribution of drilling events in diagrams in different cases and different stratigraphy. To specially understanding the drilling events, you can build a map of burst paths. Also, to estimate the position of drilling events relative to azimuth, deviation and vertical depths, it's possible to build all stereoplots as well as separate 2D plots between depths and deviation, depths and azimuth, deviation and azimuth. As can be seen in the 2D graph on the right part of slide, the largest number of drilling incidents occurred in the direction of maximum horizontal stress. It's also possible to build 3D trouble plot in the depths, deviation and azimuth axis. The next topic is well researching analysis data. This topic includes reservoir flow testing, non-reservoir closure pressure data and another data, frictional pressure loss during fracture propagation and pore pressure measurement. And the pore pressure analysis is an important steps in the evaluation of initial data in geomechanics. When drilling, the pressure difference between the wellbore and the surrounding formation leads to the invasion of mud filtrate into the formation, while solid particles accumulate in the wellbore wall, creating a filter cake. Within the wellbore, the pressure is maintained at a hydrostatic level, but it rapidly decreases across the filter cake, and then gradually drops to the original pore pressure at a certain distance from the wellbore. This is called as supercharging effect. In order to estimate of number of low quality of supercharged pore pressure measurement, you can build a diagram, table and plot points on the well section. The next object of the analysis of initial data is the analysis of XLOT. XLOT, this is extended leak-off test, and it's provide information about closure pressure that equal SHmin. We discussed it in lecture number 05. In addition to XLOT, fracture closure pressure information can be obtained from step right test and step down test. What's different? The step right test is performed to identify the formation breakdown pressure and fracture closure pressure. The concept behind the SRT involves gradually increasing the injection rate in equal time intervals, which allows a fracture to initiate and grow. This leads to minimal increases in bottom hole injection pressure as the rate increases. The fracture closure pressure can be determined by finding the intercept of the fracture line and zero injection rate. On the other hand, the step-down test is implemented to measure pressure losses in the perforation and near wellbore region of fractured wells, primarily due to tortuosity. Consequently, the step-down test offers valuable insights that are crucial for the effective design and execution of the primary fracturing treatments. This is a typical procedure for step right test. On this slide you can see the comparison table between XLOT, LOT and formation integrity test. As you can see here, the most informative method is XLOT because it gives information about fracture closure pressure. XLOT data can be used not only to estimate the minimum horizontal stress, but also to estimate the maximum horizontal stress as shown in the figure. So the maximum horizontal stress pressure in a vertical well can be recalculated from the fracture breakdown pressure and the fracture closure pressure, taking into account the tensile strengths. The next object of analysis is the assessment of friction losses in the ejection well. The following types of losses are observed in the process of injection. First, friction from sensor to perforation, number 1. Number 2, friction in the perforation zone. 3, tortuosity of the fracture. 4, friction along the fracture. 5, hydraulic head. 6, increase of SHmin due to increase in PP during injection. PP is this pore pressure. And 7, reduction of SHmin due to reduction of temperature during cold water injection. This is typical injection well scheme and typical friction table. Friction in perforation and fracture is difference between fracture propagation pressure and instantaneous shut-in pressure, and net pressure is a difference between instantaneous shut-in pressure and fracture closure pressure. And the final topic is database, is a conclusion of our lecture for today. So to summarize this slide is a result of everything we talked about above. This slide summarizes information on all geological, seismic, geophysical, log, core data necessary for the construction and calibration of geomechanical model, and it represents in a single table. The conclusions are made about the completeness and fullness of the dataset, selected offset wells, the number of necessary studies is described, and the spatial distribution of offset wells is given. This is reference, and thank you for attention.